All right, so this is what's on the handout. It's talking about the absorbance spectra that you can generate from your VASP file. So I was planning on just ignoring the directions because they are in your manual, but I will quickly rehash it. One of the important things is that you have a state file generated, and it needs to contain the right number of states. So there is a command somewhere else where you take things from the outcar, you sort of do a word search, take some lines, and then make them into the states, but there will be extra lines. So you just sort of need to delete it, so you just have all the orbital levels that are occupied and unoccupied, and that's all that's in the states file. You will rename it to input overlap, you'll name it energy population, and then you will also make a new file in Nano called input overlap with 3 lines. 1, the number of states, so in this case it would be 40, and then 1, so just 3 lines, very, very short. The next command that you will take from the bin is the oscillator strength dipole V3, and this will generate a number of files. One of those is OS strength, and you'll want to do a word count for that because that will come in. It's important for the next operation. And then you'll run another program from the bin, Spectrum IMP3, and it will ask for a number of things. The first one is the number from the word count that you did on OS strength, and then the energy minimum and maximum that you'd like to see for your particular spectra, and then the HOMO number of the orbital. So in the previous example, you look at where the highest number that has 2, so in this case it would be orbital number 32. And the next step is to pick the appropriate program for the spectra that you would like to produce. And that all depends on what you're trying to correlate it to and what sort of units you'd like to see it in. So this is the same information, but it's just different units and a different sort of layout. So in wavelength, as you know, the shorter the wavelength, the higher the energy it is. So this peak here, right around 400, is the same as this transition energy around 3 electron volts. The electron volts is convenient if you're doing electrochemical data because that is in, the units of that is milli-electron volts, so it's the same units, easier to correlate. If you're doing cyclic voltammetry, you can see where you're putting the electron in at one particular energy, where you're taking it out at a different energy. That difference will help you to figure out which transition it is. But if you're doing spectroscopy, UV-vis spectroscopy, all of the spectrophotometers that we have in the department are in wavelength. So that is important if you're, again, if you're trying to correlate this to your research, that you pick the right units. And there's 2 different programs that you can get from the bin. You'll use NuPlot because it's the most convenient. If you want something else, you can figure out how to do that in Excel or Origin. I have not. I haven't really played around with that yet. But the difference is, if you want the wavelength, you'll have the little nanometers at the end where this is just blank. And then you'll convert the file into a PDF. And then no matter what it is, you'll transfer that PDF from the HPC to your local computer so you can view it. And then you can open it up, copy that image, put it in whatever format you want. You know, if you're submitting it to a journal, it might be in Word, or if it's in PowerPoint, you might copy it from there. So what is the OS strength file anyway? So one of the things that I talked about before is the word count, and that's the number of lines. For this particular example, it was 256, and where that arises from, I have 32 states here that all have electrons, and then I have 8 more that don't. So essentially what it's doing is it's taking a populated state and it's moving an electron into an unpopulated state. So 32 states going into 8 different states, so 32 times 8 is 256. And the OS strength, it's every transition. So you see, you have the E initial, so this is 6, it's going to 36. The difference in energy, which you might be able to tell from here, because it says all the energy, it's that number. So 6 to 36, that's a pretty large transition. 31 to 33, that's a much smaller energy difference. This is the number of electrons in the initial and the number of electrons in the final. So it's 2 and 0 for this because all the electrons are paired up, so there's no unpaired electrons in this particular system. And then this number, it seems to be very important because this is how it's sorted. You have very large numbers here and small numbers there, and it's not the difference in energy because the difference in energy is sort of all over the place depending on transition. So what could this possibly be? I believe that it does relate to the Einstein coefficient. I'm not totally sure. But what that is sort of the probability of an electron being absorbed into a system. Not all the light of a wavelength that is appropriate for absorption will be absorbed. If that was the case, it would be very strange because everything would be either totally absorbed or re-emitted. So there is sort of a probability associated with a photon of a correct wavelength being absorbed by a system, and that is the absorption constant, which is one of the 3 parameters that is sort of outlined by oscillator strength. This is the constant. Those are the units. And that can be related to the oscillator strength, which is F12, and there's other equations that you can find as well for other kinds of interactions between light and matter. So there's spontaneous emission and stimulated emission. So those are both light coming from like the emission of light, but this is the absorption of light. And another thing that I'd like to talk about is the Frank-Condon principle. This is, as far as I can tell, this is sort of one thing that's not included in this system because it's strictly energy levels. So different electronic transitions, but going from this state to this state, that's just one electronic transition, but there's actually many vibrational sublevels in there. And you can actually have multiple different energies being absorbed because it might be absorbed to this level or to this level, which is a higher energy, so it would be a shorter wavelength. But what this talks about is there needs to be a good overlap. So if you think about it vertically, how much of this, the area under the curve there, is matched by that. And if there's more overlap, it's more likely that a photon will be absorbed. And then emission, we'll talk about that later. This is pretty much strictly absorption. Yeah, any questions?
Okay, let's thank Joe.